because there are no confluences downstream, first of all. So if you measure the river flow at Ponte Lavoscuro or the river flow at the delta is more or less the same, but you know that the Po River is braiding close to the delta. Braiding meaning that it starts dividing in many courses. So you need to stay a little bit behind the delta, upstream, and also you need to stay a bit upstream in order not to get the effect of the sea level rise, because you need, you know, for the alternation of the, I don't remember the name in English, of the marée. Yeah, I can't remember it now. So for the alternation of the marée, you have changes in the sea level, and when the river flow is subcritical, is a corrente lenta, it is influenced upstream. So once that the sea level raises, also the level of the Po River raises, of course. There is an influence upstream. So if you want to measure the river flow, you have to go back upstream until you don't get this influence. Because, you know, when the sea level raises, you have a return flow from the Adriatic Sea to the Po River. So you can't measure the river flow reliably. So for the Po River, the closure section is conventionally located at Ponte Lavoscuro, and there they started to measure the river flows a long time ago. And from the 1st of January 1920, we have daily measurements of the river flows of the Po River at Ponte Lavoscuro. And this is therefore probably the most important river flow series that we have in Italy. And I just want to show it to you. This is the series. You see that it's bounded below by 0, of course, and the maximum river flow is about close to 10,000. These are, important to say, daily averages, not peak flows. The daily average is always lower than the peak flow. For the Po River there is no big difference, but the daily average is always lower because the peak flow is an instantaneous event. Okay, so this is the series. And you see it's longer, it's extended until December 31st, 2009, so the number of observations is about 32,000. And let's look at the autocorrelation function. And let's put an option here. Let's put the maximum value of L. Let's put 20. So let's look how it looks. You see this autocorrelation function to compare with the one that you have seen before. You see the blue lines again, and you see that it starts from 1, but in this case you see that there is memory, because you have values for the autocorrelation coefficient that are significantly greater than 0. Let's try to see what happens for increasing values of the lag. Let me put 365 as maximum lag. This is the result. So indeed what you see is a slow decrease of the autocorrelation function until a delay, a lag of about 100. Then you have the autocorrelation function getting back higher, then decreasing, and then higher again in correspondence of the annual cycle. So what's the reason why there are these increases after a while? Because you would expect that correlation, memory always decreases if you go far in the past. Instead, it seems here that there is an increase after about 6 months, you see, and after 1 year. What's the reason for that? The reason is simple. Because river flow data, as many hydrological data, are affected by seasonality. Seasonality means periodicity. It means that after 1 year, you have like a repetition of the statistical behavior. You have that the process repeats itself year by year in a similar way. For instance, we always expect drought flows in the summer and winter, and we expect higher flows in April, June, and October, November. So every year you have a kind of repetition which is never equal to itself, because of course there are any year changes and peculiarities, specific behaviors, but the general pattern is repeating every year. And therefore the effect is that it seems like there is a memory after 1 year. So you can understand why the autocorrelation function goes up after 1 year, and the reason why it goes up also after 6 months is that our climate, the climate of the Po River, is characterized by a 2 peaks behavior, 2 peaks pattern. And one pattern is, as I said, in May-June, one peak is in May-June, and the other peak is in October-November. And then you have 2 droughts, one during winter and one during summer. So it looks like the system has also a memory after 6 months. So this is the reason why you see from the autocorrelation function that there is a peak after 6 months. So you see the autocorrelation function indeed gives important information in the process. And to be able to read, to capture this information is important. Now, you might be curious about the probability density for the Po River and Ponte Lato Scuro, so let's here it is. You see that it's not Gaussian because you see a long tail on the right-hand side, which is expected because hydrological variables, rainfall and river flows in particular, are characterized by a long tail in correspondence of the upper values. So you see, it's not Gaussian, but what happens if we take the logarithm? Maybe it's closer to Gaussian, as I said. Let's see. Just by saying log, let's see what happens. You see that we are getting closer to Gaussian, as I said. It's not really Gaussian, but not bad. Okay, I think that I can turn the projector off for the moment. And my recommendation is to always play with data, with numbers. Because we are engineers, we have to be capable of playing with numbers. And also it helps us in gaining a better understanding of statistics. I think you might be bored by statistics, but you know, it's really important, as you will see, for water resources management, because we cannot write deterministic models in hydrology, because we have limited understanding, as I said, and also there is always uncertainty, which cannot be eliminated, and therefore you need statistics. Now, let me now go back to the theory, and let's try to understand some more about stochastic processes, because as I said, when I want to generate data by reproducing also the memory, I cannot just use probability distribution, I have to use stochastic processes, and I said that they preserve not only the probability distribution but also the memory. And I said we will make use of linear processes. Before we start talking about processes, I would like to make a premise which is related to a very important detail and some definition. Definition are quite boring. The detail, I think it is interesting. So let me now introduce the interesting detail. And the interesting detail is related to a physical meaning of the probability of not exceedance. So we define the probability of not exceedance as f of a given outcome of the random variable, this is lowercase x, and the probability of not exceedance has one more important physical meaning. It is univocally related to the return period, which is a very important parameter that we use when designing structures. Probably you heard already about the return period, which is called tempo di ritorno in Italian. And first of all, let's see what is the return period. Let's consider a given event or a given forcing to a structure, like a peak river flow. A peak river flow is a forcing on bridges and on other civil engineering works that interact with the river. Any civil engineering work that interacts with the active river must be designed by referring to the peak river flow that can stress it. This is particularly true for bridges, it's true for fluvial defenses, it's true for levees, argini, and it's true also for sewer systems, fognature, so not only with civil engineering structure interacting with the river, but also for civil engineering structures that have to drain rainfall, like sewer systems, or even the pipes that in our houses, the grondaie, bring the water from the roof to the sewer system. They must be designed against a design rainfall, which is determined for a given return period. And so what is a return period? The return period for a given forcing, for a given event, like a peak river flow, is the average time that occurs between two events that are greater or equal to the given one. I make an example. First of all, I repeat the definition. The return period of a given event is the average time that passes between two events that are greater or equal than the given one. Average time that passes between two events that are greater or equal than the given one. Let me make an example. For the Po River, the return period of a river flow of 10,000 cubic meters per second at Ponte Lacoscuro, so this is the given event, peak flow of 10,000 cubic meters per second at Ponte Lacoscuro. The return period is about 100 years. It means that on average, we have to wait 100 years between two events at Ponte Lacoscuro that have a peak river flow greater or equal than 10,000 cubic meters per second. So if I have a Ponte Lacoscuro, I see an event that is 11,000 greater than 10,000 cubic meters per second, I am expecting that on average I have to wait 100 years before seeing the subsequent event that is greater or equal than 10,000. on average is extremely important, because if you forget to say on average, you would say it is the time that passes between two events. Why? This is not true. This is absurd, as you can understand. You are not sure, once that you see a peak flow, that 100 years passes before seeing another one. And the practical demonstration is again the Po River, where we experienced a 100-year record period flow in 1994, and the subsequent one was in 2000. So only 6 years passed between two peaks that had a record period of about 50-100 years. This is because you wait on average the record period, which means that you may wait shorter or longer for a specific case. But you understand that the record period, the concept of record period is extremely important in engineering, because when you design engineering work, even very important like a dam, you have to adopt a forcing against which to design the work itself. And this forcing, of course, in the case of events that are not certain, should be computed statistically. And therefore you define the record period. To give you an idea, when you design sewer systems, the record period is about 10 years. When you design roads I mean hydraulic works to drain roads, is about years. I don't know how to say in English, but I mean the cunettoni, tombini stradali, this kind of works, the record period is about 20-30 years. The record period, is about 100-200 years for bridges. The record period is about, depending on the country, 500-1,000 years for dams. You see that the record period increases, as we expect, with increasing consequences of a hypothetical failure of the work. So if you have a failure of a sewer system, you just get your feet flooded. In some cases it's worse, but on average it's not a problem if you get a failure of a sewer system. Or let's say it's not a big problem. If you get a failure of the drainage system of roads, you can get some people killed, because if they ride with the car at high velocity, they find water, this is a problem. Also, we had some people killed for a failure of the drainage system of an underway. I don't remember when, but it was some years ago, a couple of accidents occurred for underway flooded. If you get a failure of a bridge, of course, the potential consequences are very important, and for a dam, of course. Okay, so what is the relation between the record period and probability? They are related. We can understand they are related, because if we say that the probability of not exceedance is 99% for an event, it means that if we make 100 experiments, we expect that just one experiment gives a result that is higher than the given event. This is what probability says. Probability of not exceedance of 99% means that 99 times over 100 we get lower values for the given process. So it is related to the reference period. Precisely, the relationship between probability and return period is the following. Fx, probability of not exceedance of a given lowercase x event, is given by tx minus 1 divided by tx. This is the relationship. But is the measure of unit of this time. This is important. Here, the return period is expressed in number of experiments. So if you make 100 experiments, the return period again is expressed in terms of number of experiments. So if you are dealing with daily data, so you have one experiment per day, the return period is expressed in days. Because of course, the experiment is one per day, so if you get 10 experiments of return period, 10 experiments means 10 days. If you deal with annual data, annual maxima, for instance, the return period given by this relationship is expressed in years. Basically, if you are asked to design a bridge for a return period of 200 years, what you have to do is to estimate the probability distribution of the river flow and compute what? The return period, depending on the return period, the probability of not exceedance. And then, for the given probability of not exceedance, you compute the inverse of the relative probability distribution to get the quantile that corresponds to the given probability of not exceedance and therefore return period. So you have to estimate the probability distribution of the river flow, and then you get the return period, you compute the given probability of not exceedance, and then feed your probability distribution with the probability of not exceedance, and you get the quantile. This is what you are expected to do to design a bridge. So you see that statistics is really important. Now, this is the detail. Return period is important. I very often ask at the final examination what is the definition of return period, why it's useful, how to compute it, depending on probability. Okay, now let me introduce a few definitions, as I said, before passing to an example of stochastic process. And it's more difficult to learn the definition than the process itself, because you will see that the process is very simple. Now, the definition. First of all, an easy definition. I talked about memory and correlation. There is a term that is used to say that the data have no memory. They have no correlation, and the term is independent. If we say that the process is independent, this means that each outcome from this process does not have any impact on the other outcomes. There is no memory, but the definition, the correct definition is that each outcome does not have any impact on the others. So if we say that data are independent or a process is independent, now you know what it means. Okay. Of course, now we are talking about processes, so we are implying implicitly that we are dealing with dependent data, data that have memory. Okay, now a second definition which is extremely important. Stationarity. It refers to a process. What does it mean, stationarity? Intuitively means that something does not change. Intuitively. And in fact, stationarity of a stochastic process means that the statistics of the process do not change along time. Stationarity of the process means that the statistics of the process do not change along time. In practice, what it means, this property, it means that if you have a long realization of a process, like the Po River that we have seen before, it started from 1920 to 2009, and as you have seen, there is this kind of series. Stationarity means that if you compute the average, for instance, but any statistics, but let's focus on the average, in this window, along this window, from like 1920 to 1930, you get the same value as you computed the average in the recent past. Statistics are not changing in time. This is stationarity. And it's, of course, of a process. You have a sequence of random variable, a family of random variable, which is a process. And if you compute the statistics of this process in time, they don't change. Of course, the process changes, but not the statistics. And also, of course, keep in mind that when you compute the averages, they are estimators. So they are estimates, sorry. So they are averages of a series of numbers. They are never equal, strictly speaking. They are similar. They are theoretically equal. They are equal in theory. But from a practical point of view, they are similar. Stationarity is today very much discussed because you know that in view of the presence of possible climate change, some people are claiming that natural processes are changing. Changing means that there is no stationarity. For instance, some people say that the floods are increasing in severity. It means that there is something non-stationary. Or some people say that the average of the river flow is decreasing, or the average of rainfall. And therefore it means, again, that there is no stationarity. And, you know, this is a delicate issue because stationarity is very much important for the civil engineering design. Because usually what you do to understand the process is to look at the past. And if the past is no more representative of the future, of course we get in trouble. So it's very much important, this concept of stationarity. Let me introduce another definition, which is the definition of realization of stochastic process. What is a realization? Intuitively, you already understood what it means. It is the counterpart of the term outcome for a random variable. If we speak about a random variable, you use the term outcome to mean a random extraction from the population of the random variable. The stochastic process is a family, as I said, of random variables. So when you pick up, let's say, outcome, you have to pick up not just a number, but a sequence of numbers. And this is the realization. The realization of a process is, again, the collection of the outcomes from the single random variable that compose the process. So if we admit that the sequence of flows of the Po River is a stochastic process, then we can say that the observed series is a realization. Unfortunately, nature has just one realization. But if we define the process like the sequence of 1 year of flows, then every year is a realization. It means that, of course, in this case, nature has many realizations, but this is just an idealization of what nature means for us. So, a striking difference between our models and nature is that with our models, we can perform many realizations. We can get many realizations. Nature gives just one. And the length of the realization is as long as we want from a stochastic process. Okay, now there is the last definition, which is probably, from an engineeristic point of view, not as useful as the previous ones, but it's very much important, and also I don't want you getting lost when you hear words that you don't know, because also this gives, when you heard somebody speaking about an issue, and you don't recognize the terms, this is a very important obstacle for you to understand the topic. The topic might be very easy, but if you don't understand the terms, this is a problem. And you get the feeling that the topic is very hard, maybe too hard for you to learn, but instead it's just a question of knowing the definition. And this is particularly true for statistics. Statistics is very simple, I can tell you, it's very simple, but the problem is that the words are not familiar. We are not familiar with the terminology. So, when we heard somebody starting to talk about stationarity, independence, stochastic processes, we don't know the meaning of the words, and then we get the feeling that it's something that is too much for us. It's not like so. If you are an engineer, you can understand statistics because it's very simple, but the problem is the terminology. So this is the reason why I want you to learn the basic definitions, and this is also why I want to explain what ergodicity means. Ergodicity, this is really a nasty word, but indeed the concept is very simple. From a practical point of view, let me first of all tell you the practical meaning of ergodicity. Ergodicity in practice means that if you have observations from a process like river flow and you compute the mean is correct. This is the practical meaning of ergodicity, meaning. And it's not always true, because we have small series of data. Maybe that for one river we have just 2 years of observation. So if we compute the average, we are not sure that the average is correct. And then the definition of ergodicity comes into play. We say, okay, let's assume that the process is ergodic. If the process is ergodic, even with a small series, I can estimate the statistics. This is the practical meaning. And of course, it's not always satisfied. But it's a definition that is important. If you talk with a statistician and you say, your assumption of ergodicity is not, maybe it's not satisfied, you don't understand what ergodicity is, you get lost. But it's very simple. It means just that the statistician is telling you that you have a small sample, too small sample of data, you need more data. This is just what he wants to tell you. So, ergodicity means this. The definition is a bit more complicated, and I will propose not to enter into the definition. Just the meaning is enough for us. You will find the definition on my slides. It's not important that you learn it. Okay. I think that now we are ready to introduce stochastic processes. This is a bit more, probably more comprehensible from a practical point of view. I suggest that we stop 15 minutes and then we go on.